Let's look now at a second Fourier transform, the Fourier transform of a Gaussian. We'll define our Gaussian function like this, e to the negative x squared divided by sigma squared, which means the width of our Gaussian function is proportional to sigma. And we define the width either as the full width half maximum, so it's the width of the Gaussian when you are at half the peak height, so the peak height here is 1, so that's half, or the 1 on e width, where you look at the width when you're at 1 divided by e of the height, and the width there is just 2 sigma. So the Fourier transform is defined like this. We're going to substitute this function f of x into this integral, and we get something that looks genuinely difficult. But there are some tricks we can use to make it actually quite doable. First trick is if we combine these two exponentials together, the combined exponent would be x squared on sigma squared minus ikx, negative out the front there. And we can rewrite this as negative the square of this thing in brackets here minus something that does not depend on x. So this term here, the sigma squared k squared on 4, does not depend on x at all. So when we write e to the power of all of this stuff, this can become a factor that we can bring out the front of the integral because it doesn't depend on x, so it doesn't need to be in the integral. Now our integral is e to the negative something in brackets squared. We can do a change of variable. We can write q as x on sigma, ik sigma on 2, that's this thing in the brackets here. And then we can have dq is equal to 1 on sigma dx. Doing that change of variable in the integral leaves us with this integral here. So we've got a sigma out the front from the change of variables, the factor we extracted previously, and now just the integral from negative to positive infinity of e to the negative q squared dq. And this is just the integral of a Gaussian, which we can look up. That'll be root pi, which gives us that the Fourier transform, f of k, is sigma root pi e to the negative sigma squared k squared on 4. And so what's interesting about this is that the Fourier transform of a Gaussian is a Gaussian. The original Gaussian here had sigma squared on the bottom, and now we have a factor of sigma squared on the top multiplying k squared, but it's still a Gaussian. Gaussian in space, Gaussian in spatial frequency k. And just as in the case of the top hat, the shorter the function is in space or time, that is, if we make sigma smaller, then the wider the function becomes in frequency space, k or omega. So a smaller sigma here will make the function wider. So to look at that explicitly, the full width half maximum of our Fourier transform is proportional to the inverse of sigma, and the 1 on e width proportional to the inverse of sigma, whereas here the width is proportional to sigma. So the narrower this becomes, the wider this becomes, and the reasoning is the same, that if you make this function have a really sharp, narrow peak, you need very high frequency components to capture that behavior, making the spread in frequency space wider.